Hi everyone, today is March 26, 2019. This is third episode about automata theory and implementation in C++. Last few days I implemented C++ library for Deterministic Finite Automata and Nondeterministic Finite Automata, also a lot of helper functions for automata theory. Please double click this link. When download is completed, please unzip the file. Then copy this folder, paste it to your working folder. Double-click the folder path, copy, start Visual Studio 2017. From File, Open, Solution, paste the folder path, \, Enter, then select the solution. In the Solution Explorer, click this button, double-click this file. Then press Ctrl F5. Then you can find the output like this. Then close it. If you open this file, then the output is captured to text file and opens like this. For example, in this automata CPP file, scroll down. If I disable this function, Ctrl F5 again, then the contents of our file is empty. And if I want to test one function, disable this, then Ctrl F5. Then the result is displayed like this. Then the output is captured in text file like this. Back again. If I enable this function again and run it once again, then all the output is captured here. This is DFA Deterministic Finite Automata initialization example. And this is NFA to DFA compact conversion demo. This is NFA table. And this is also NFA to DFA conversion with full subset construction. This example is from this book, Introduction to Automata Theory, Language and Computation. From this book, page 61, the example is like this. Okay? Most of these examples are from this book, Automata Theory, Language and Computation. Most examples are from this book. For example, this is exercise 3.2.3.2, page 66. This NFA is converted to DFA using full subset construction. These are all converted using software. Then this is another way, compact conversion. These are all generated. So in this example, NFA to DFA more example, we first create NFA, then convert to NFA to DFA, then minimize DFA states. These are the result. For example, I disable this, I enable it, Ctrl F5. We can see the result like this. I will compare side by side. This is the example. Output of this example. NFA to DFA more example. NFA to DFA more example. Create NFA. First we initialize NFA, class NFA. This is initialization process. These are the state table, transition table. this is input values. Then we display the NFA like this. This is displayed NFA. Then we create DFA from NFA. This one. DFA is generated using this function. Then this table is generated using this function. NFA, DFA to compact conversion. Before minimization, this is before minimization. And this table is after minimization. This is after minimization. So these are generated using the function. In the Solution Explorer, class view, talk playpen namespace, you can see the functions used to implement these things mostly are set operations. In the Solution Explorer header file, most operations in theory of automata are set operations. I first developed this library in 2017, February 20, and I edited today, it should be 26. I made more changes today, for example, 26, 2019. I implemented my here, narrowed theorem. So these are all my implementations, mostly are set operations. How to compare set, how to sort set, how to union set, all these are set operations that I use in this development. And this file contains automata, class NFA and DFA, etc. In this case, it has class DFA. This is class DFA. And this member, we are using these two functions, DFA and NFA. And I try to explain as thoroughly as possible. If you have questions, please leave your questions and comments. Now I will tell you how to make setup for these solutions. In the Solution Explorer, new project, 01, hello, DFA, NFA. Click OK. Right click new project, set as startup project. Right click once again, properties. Make sure all configuration, all platforms selected. From C++ language, select C++ 2017 standard. Click apply. From general, edit, $ solution dir include, then click OK. Apply. In the linker, general, copy this text, build event, post build event, click this button, edit, quote, paste, quote, then $ solution, project dir, then it should be resolved like this, then output txt, quote, like this. It should be resolved like this. Click OK. apply. OK. Then right click, add existing item, go up in the include folder. These are all libraries I developed recently or in the past. Click automata, emun matrix, then set operations. I actually use more libraries internally, but these are good enough. Click pch header file, include talk play fun automata. This file includes all other files too. Click here. We don't need this. Auto stream std cout auto nl new line character auto nl to new line. Then we remove these things. Now we create void test DFA NFA for the first time. I will close it, copy this function name, paste it here. Step 1, define types using symbol t int, using state t character. The type of symbols or the element type of the alphabet. The type of state Q. Using NFA T, we define non-deterministic finite automata type like this: talk, play, fun, NFA, symbol T. We have to provide a symbol type and state type. We defined here, it will be int, then state T, this is state type. We defined NFA class. Right click, go to definition. For example, in this file, talk, play, fun, automata.h, this class is defined. This is symbol type. State type is index or state is a DQ. We defined symbols like this. This is table. Transition table type is defined like this. I will explain more about this class, how to implement it in future sessions. Now we define the type, then we define an instance, NFA, T, NFA. We can provide two strings for header and the title. This is title, NFA initialization. This is title by Thomas Kim. This is footer text. These are optional. The first step is NFA. We have to set first symbol. We have to define symbols like this, 0, 1. Because symbol type we defined here, symbol T is int, the type of input symbols. NFA set 2. We need to set start state and accept states like this. Start state will be P and accept state will be Q and S. So there is two accept state. The start state Q, S are the accept states. NFA set 3. We now have to define transition table like this. Please note that it should be a set like this. Then we define each element. Q, S, Q, R, Q, R, S, P, This is empty set P. We define the states. Step 2, define an instance of NFA. Step 3, set 1, 2, 3 for initialization. Now we can display generated NFA like this. Stream. We define the stream cout here. NFA defined as below. NL2. NL2 is 2 carriage return here we defined. Now we build and run this function. Control F5. Sorry, we forgot to display NFA. I will put a carriage return here. Control F5 once again. So this NFA defined as below this text, then NFA is initialized like this. So we have 0 and 1, 2 symbols. These are integral type int, and these are state P, Q, R, S. P is the start state, Q and X are accept state, then QS, Q. We fill the transition table with this function, set3, transitions. Then we displayed the result. I will put another carriage return here. Convert NFA to DFA using full subset construction. Or DFA, NFA, we create DFA like this. We need to provide false for full subset construction. Now we can display like this. Stream DFA NL2. Now we run it. Control F5. So this is NFA we initialized. From this NFA, convert NFA to DFA using full subset construction. This is message is displayed. Then the table is created. DFA is created. Then this command displays the result like this. Two tables. They are actually the same. Now we try another one. Stream convert NFA to DFA using compact subset construction. NL2 or DFA compact. NFA, from NFA create DFA. See, default value is true. Stream DFA compact. We display the result like this. NL2. Control F5. So I already explained the upper part. Now let's see. This is compact. NFA to DFA using compact subset construction. Or we can open this file. Right click. Add existing item. From hello DFA NFA output. This file is generated. Okay. So if we compare, this is for full subset construction. This is for compact subset construction. This is DFA. This is also DFA. They are exactly the same thing. Actually, they define the same DFA converted from this NFA. Or DFA compact. Now we can minimize the state. Minimize states. Stream minimized DFA NL2 stream. We can display this once again. NL2. If we run it, I have to close this function. run it. Minimize DFA. We can open this file again. So this is before minimization. This is converted DFA before minimization. This table is now minimized like this. It has minimized. In case of minimized, there is 5 stages: 0, 1, 2, 3, 4. Before minimized, there is 7 stages. After minimization, there is 5 stages. This example is actually from this book, Introduction to Automata Theory and Language Computation. This is actually exercise page 66, exercise 2.3.2. Now I will build once again. Control F5. Now you can find all the result like this. To implement this class, to implement DFA, Deterministic Finite Automata, and NFA, Nondeterministic Finite Automata, we use a lot of set functions, set operations. For example, we have to use build subset and a lot of other set functions as well. Difference, intersection. In future sessions, I will explain how to use these set functions. Implementing these DFA and NFA can be a little bit challenging if you do not know how to manipulate sets in C++. If you understand and know how to manipulate sets or how to do set operations in C++, implementing DFA and NFA, these are not that much complex or difficult. For example, NFA, if you click this class, then you can see create DFA states. Using this function, I converted from NFA to DFA. And also in DFA here, I use in this minimize states my-hill narrowed function. Most of this code is about set manipulation. If you can operate sets properly in C++, implementing algorithms in theory of automata is not that much complex or difficult. In future sessions, I will explain how to use these libraries, how to implement these libraries in C++. Please note that all these files and functions code is my own development. In the solution folder, include folder, these are all libraries I implemented by myself, so you can freely use them. I will explain in future sessions how to implement algorithms in set operation and theory of automata. I will post this script in the description section below. You can click this link to download the source code. Please subscribe to my YouTube channel. Thank you for watching.